All right, let's dive right into one of the most mind-bending ideas in all of physics, entanglement swapping. This is a quantum magic trick that lets us link up particles that have never ever met. They haven't interacted, they haven't shared a past, and maybe, just maybe, they didn't even exist at the same time. This is a concept that truly messes with our ideas of cause and effect. So let's get into it. And that really gets us to the heart of it, doesn't it? The big question for today. Can two things be fundamentally connected without ever existing at the same moment? I'm talking about linking a particle that's already gone to one that hasn't even been born yet. It sounds like something straight out of science fiction, right? Well, as we're about to find out, the answer is a very, very weird yes. Okay, so before we can start connecting particles across time, we've got to get the basics down. We first need to understand the fundamental trick that makes it possible to link them across space. Let's break down the basic quantum swap. This is really the first step in bending the rules of reality as we know them. So what is entanglement swapping, really? Well, imagine you want to create a quantum link between two particles. Let's call them A and D. Now, here's the catch. They have zero shared history. They didn't come from the same place. They've never been near each other. They're complete strangers. So how in the world do you get them connected? It's kind of like a three-step recipe for breaking reality. First, you start with two totally separate entangled pairs. So particle A is linked to B, and particle C is linked to D, but there's no connection between the AB family and the CD family. Next, you grab one particle from each pair, B and C, and you perform a special kind of measurement on them together. It's called a Bell state measurement, and you can think of it as asking them a question that they can only answer as a team. And this is where the magic happens. The very instant they give their answer, that one action forges a brand new entanglement link between the particles left on the outside, A and D. Just like that, they are connected.
And look, this isn't just some wild theory on a blackboard. This was actually done back in 1998. That experiment was a huge deal. It proved that entanglement isn't necessarily about sharing a past. It's about how quantum information is measured. And that one discovery, well, it laid the groundwork for all sorts of future tech we're still chasing, like quantum teleportation and a real quantum internet. Okay, so linking particles across space, that's weird enough. But what happens when we start messing with the timing of these measurements? This is where things go from weird to completely unbelievable. What if a choice you make right now could actually reach back and determine whether two particles were entangled in the past?
So let me walk you through the setup of this famous 2012 experiment. You've got two people, Alice and Bob. They each get a particle, they measure it, and that's it. Their part is done. The data's in the can. Then, sometime later, and this is the key part, a third person, Victor, gets the partner particles. And only then, after Alice and Bob are long finished, does he decide how he's going to measure them. And this is the part that just breaks your brain. If Victor decides to do that special Bell state measurement, when you go back and look at Alice and Bob's old data, it shows all the signs of quantum entanglement. But if Victor chooses a different kind of measurement, that exact same past data shows nothing. Just random correlations like you'd get from flipping two coins. No connection at all. A choice made in the future literally defines the kind of connection that existed in the past. Don't just take my word for it. The scientists themselves put it perfectly. They said entanglement can be produced a posteriori. That means after the fact. It's created after the particles have already been measured and might not even exist anymore. That link, it wasn't set in stone back then. It was just waiting for a future event to write it into history. Now, you're probably thinking it can't get any weirder than that. Oh, but it does. What if we push this whole idea to its absolute logical extreme? What if we tried to entangle a particle that is already dead and gone with another particle that hasn't even been created yet? So an experiment in 2013 did exactly that. Just follow this timeline. It's wild. At time 0, photon 1 is created. It's immediately detected and destroyed. Its entire life is over. Then, sometime later, a totally new particle, photon 3, is created. And only then do the two surviving partners, photon 2 from the past and photon 3 from the present, finally meet and get measured. The result? The data for the long-dead photon 1 showed it was quantum entangled with a particle from that second pair. The authors say it right here. One photon was detected before the other one was even created. This isn't just non-locality in space anymore. This is non-locality across space-time itself. It's just staggering. So, what's the point of all this temporal weirdness? Is this just a philosophical party trick for physicists, or can we actually use it for something?
Well, this is where the story pivots from mind-bending physics to potentially world-changing technology. Let's just pull all these threads together for a second. As we've seen, each one of these experiments has chipped away at our common sense assumptions. First, we learned particles don't need a shared past. Then, we saw that the nature of that past is actually flexible. And finally, we found out they don't even need to exist at the same time. So the next logical step, right, is to find a way to control this whole process. And that's what turns this weird physics into a powerful tool. See, the ability to link quantum states across space and time is the key to solving one of the biggest problems in quantum communication: distance. Entanglement is super fragile. It usually dies out over long distances. But by using entanglement swapping, we can build quantum repeaters, little stations that can daisy chain these short, fragile links together to create one unbreakable connection across a whole continent. This is the basic blueprint for a future, totally unhackable quantum internet. Now, the piece of tech that makes this all possible is something called a quantum memory. Just think of it like a quantum waiting room. It's a device that can catch the quantum state of a photon, hold onto it for a little bit, and then release it when it's needed. This ability to store entanglement is what lets a network connect different links that weren't created at the exact same moment, which is absolutely essential if you want to build a large-scale quantum network. But honestly, the technology is almost secondary to the deeper meaning here. These experiments force us to completely rethink what reality even is. You know Einstein's famous phrase, spooky action at a distance? It turns out it wasn't just about space. The universe is woven together in a way where when something happens can be just as flexible, just as spooky as where it happened. And that leads us to this pretty staggering conclusion, which physicists working on these problems have pointed out. Our entire intuition about cause and effect, this simple story where the past is fixed and it causes the future, is at a fundamental level just not how the universe works. It's untenable. The world we actually live in is far, far stranger than that.
And so we're left with this really unsettling idea. If a connection between two things can be decided after the fact, if the past isn't some fixed story but can actually be shaped by the future, well, it challenges everything we think we know. It leaves us with maybe the most profound question in all of physics. What, then, is time?